Relative density equilibrium. Anthony Riley did an experiment. As Anthony poured salt into the salt solution, the egg accelerated and moved towards the top of the glass. I contacted Anthony Riley and asked him if he could provide a statement for why the egg accelerated and moved towards the top of the glass. His reply: the egg moves because the density of the medium is manipulated. This, the salt, altered the amount of mass in the medium, and because the walls of the container cannot flex, the only place the change in mass can go is up and cause pressure that pushes the egg up from underneath. The force is pressure caused by adding mass below the egg. I repeated a similar experiment, but had the object start on the bottom of the container. The widget. The widget itself is filled with sugar solution and is made to be slightly less dense than tap water. As the glue used is less dense than water, this end of the widget is less dense than the other end. Both ends of the widget are denser than tap water. The video will show what happened when sugar was added to the medium, tap water, that the widget was in. Note, as the P900 can only record for approximately 27 minutes at a time, after 27 minutes the record button was immediately pressed again, so the video consists of 2 linked videos. In this observation, a mass of sugar was added to the tap water. The position of the widget in the fluid medium was observed and recorded. Other factors can potentially affect the position of the widget in the medium. The main factors that could have altered the position of the widget are temperature. The experiment was done in the morning and not in direct sunlight. Medium movement, disturbance of the medium. The experiment was done in a quiet room at the back of the house. The video shows that no significant disturbance of the medium from external influences occurred. What the observation visually showed. 1. When the mass of sugar was added to the tap water, the position of the widget in the medium changed. 2. The widget initially moved its position in the medium from a horizontal position to a vertical position. 3. The widget in the vertical position accelerated and moved towards the top of the medium and stayed there for the duration of the remainder of the video. Explaining what happened. 1. The mass of sugar at the bottom of the container started to dissolve into the medium. 2. The mass of sugar at the bottom of the container dissolving into the medium formed a heterogeneous mixture. That just means that the sugar was not equally distributed throughout the medium, resulting in a density gradient. 3. Density gradient. The mass per centimeter cubed of the medium is greater at the bottom of the container compared to the middle of the container. The middle of the container has a greater mass, number of particles, of sugar per centimeter cubed of the medium compared to the top of the medium. 4. There is also a concentration gradient in the container, the quantity, number, of sugar particles per centimeter cubed of the medium. There is a higher concentration of sugar particles at the bottom of the container relative to the top of the container. The mass of sugar that was at a high concentration in the bottom of the container was continuously dissolving into the medium and diffusing throughout the medium. A solute, the sugar, will diffuse from an area of high concentration to an area of lower concentration. In this situation, the sugar will be diffusing from the mass of sugar at the bottom of the container towards the top of the medium. Although this presentation will be focusing on the diffusion of dissolved sugar in a sugar solution, it must be remembered that water diffuses as well. The water will also be diffusing through the sugar solution from a high concentration of water at the top of the container to an area of low concentration of water at the bottom of the container. The diffusion of water is termed as osmosis. How do the sugar particles diffuse throughout the medium? The dissolved sugar particles will diffuse through the sugar solution water medium by their thermal motion and by collisions with other particles. Moving and being pushed in all directions, some of the sugar particles will stay in the area of high concentration of sugar particles, whilst some of the sugar particles will move and/or be pushed into areas of the water where there are less or no sugar particles. This is a reasonably slow process for the diffusion of sugar since the single particle of sugar, sucrose, has a large mass compared to the water molecule itself and other molecules that dissolve in the water. Presented is a very simplistic model of a sucrose sugar particle in water. The purpose of the diagram is to illustrate the difference in size between a sucrose sugar particle and the water particles surrounding it. Due to the size difference, the rate of diffusion of a sucrose sugar particle through the water will be slower compared to a smaller particle. Recap. 1. A mass of sugar was added to tap water and sunk to the bottom of the container. 2. The mass of sugar at the bottom of the container started to dissolve into the tap water. 3. As the mass of sugar started to dissolve into the tap water, this resulted in a concentration gradient within the medium. 4. Dissolved sugar diffused throughout the medium in accordance with the concentration gradient, from the high concentration of sugar at the bottom of the container to the lower concentration of sugar at the top of the container. 5. Due to the relative size mass differences of the sucrose sugar molecule, which has a relative atomic mass of 342, and the water molecule, which has a relative atomic mass of 18, the rate of diffusion is slow compared to another molecule diffusing through water such as methanol, which has a relative atomic mass of 34. Why did the widget initially stand up in the sugar solution? It took approximately 22 minutes for the widget to move from a horizontal position at the bottom of the container to a vertical position. What caused the widget to move in this way? Step 1. A mass of sugar is placed into the tap water. The sugar sinks to the bottom of the container. Step 2. The widget rests on the layer of solid sugar at the bottom of the container. Note: sugar did not start to dissolve on the way down. The amount dissolved is assumed to have been minimal and to have no overall effect on what was observed. The column of tap water was initially displaced in an upward direction by the layer of solid sugar that formed below it. Step 3. The solid sugar started to dissolve and diffuse into the tap water immediately above it, which immediately produces a density and concentration gradient. The density of the layer of sugar solution immediately above the sugar layer increases, which means there are more particles in an identical volume. Due to the layer's increased density, it is exerting more pressure in all directions relative to the tap water. The process of dissolving also increases entropy and results in the dissolved aqueous sugar particles having more microstates compared to when it is solid sugar particles positioned at the bottom of the container. Dissolving is an exothermic process resulting in the particles of the sugar solution and air absorbing the thermal energy, which increases the kinetic energy of the particles. This results in an increase of the entropy of the sugar solution and the number of its microstates. Step 4. The solid sugar continues to dissolve and the density and concentration gradients continue to form. The density of the layer of water immediately above the sugar layer increases, which is more dense than the sugar solution layers above it. Particles of dissolved sugar continue to diffuse from a high concentration to a low concentration towards the top of the container. Although the layer of sugar solution immediately above the layer of sugar at the bottom of the container is becoming more dense, its relative density is not equal to or greater than the density of the widget, so the widget does not change position. The widget is being collided into and pushed pressure by the diffusing particles, but the momentum of the particles and the energy transfer involved is not high enough to overcome the inertial mass of the widget, so the widget does not move. Step 5. The less dense end of the widget now has the same density as the sugar solution layer it is in and rises upward with this layer of identical relative density. Step 6. The less dense end of the widget continues to rise and stay in relative density equilibrium with a layer of sugar solution of similar relative density. The more dense end of the widget stays at the bottom, indicating that at present, no layer of sugar solution present has an equal or greater density than the denser end of the widget. Step 7. The less dense end of the widget continues to rise and stay in relative density equilibrium with a layer of sugar solution of similar relative density. The more dense end of the widget stays at the bottom, indicating that at present no layer of sugar solution present has an equal or greater density than the denser end of the widget. Step 8. The less dense end of the widget continues to rise and stay in relative density equilibrium with the layer of sugar solution of similar density, which results in it being in a vertical position. The more dense end of the widget stays at the bottom, indicating that at present, no layer of sugar solution present has an equal or greater density than the denser end of the widget. What happened? The widget went from a horizontal position to a vertical position. Note: it is appreciated that the density and concentration gradient will continue to increase, which will result in the widget eventually moving into a horizontal position. Any thermal energy generated by energy transfer will reach temperature equilibrium with the surroundings. Sugar at the bottom of the container. Dissolving, entropy increases. Sugar solution in density disequilibrium. Diffusion, kinetic energy. A density and concentration gradient continues to form. Diffusion, kinetic energy. Eventually, a stable density and pressure gradient in dynamic equilibrium will be formed. Widget at the bottom of the container in relative density equilibrium before a sugar solution forms. Diffusing sugar results in a density and pressure gradient within the sugar solution. The sugar solution around the widget increases in density, as does its pressure. The pressure from the more dense sugar solution layer underneath the widget pushes it upward. Conclusion. The widget moved from a horizontal position to a vertical position because a density and concentration gradient were formed as the solid sugar at the bottom of the container dissolved into the medium, tap water, sugar solution, and diffused. The density and concentration gradients continued to form as the solid sugar at the bottom of the container dissolved into the medium. The less dense end of the widget was pushed upward from the increased pressure from the now more dense sugar solution layer below it. As the density and concentration gradients spread upward throughout the container, the less dense end of the widget was pushed upward from the increased pressure from the now more dense sugar solution layer below it. The more dense end of the widget stayed at the bottom of the container because the sugar solution layers underneath and around the widget were not denser than the widget, and their pressure was not great enough to overcome the inertial mass of the more dense end of the widget and the downward pressure on the widget from the less dense sugar solution layers above it. Why did the widget rise up from the bottom of the container? It took approximately 5 minutes for the vertical widget to leave the bottom of the container and move upward to the top of the sugar solution medium. What caused the widget to move in this way? Step A. The solid sugar continues to dissolve and the density and concentration gradients continue to form. The end of the widget labeled A is less dense than the end labeled B. The less dense end of the widget is stuck in a relatively more dense sugar solution because the more dense end of the widget is determining the position of the widget with the sugar solution medium. The more dense end of the widget, B, is still denser than the sugar solution layer around it. The pressure from the surrounding sugar solution is not great enough to overcome the inertial mass of the more dense end of the widget and the downward pressure on the widget from the less dense sugar solution layers above it. This results in the denser end of the widget staying at the bottom, which prevents the less dense end of the widget from rising upward. Step B. The solid sugar continues to dissolve and the density and concentration gradients continue to form. As the sugar at the bottom of the container continues to dissolve in the layer of sugar solution immediately above it, this layer of sugar solution becomes more dense. The density of the bottom layer of sugar solution layer is now greater than the density of the end of the widget, B, and the greater pressure now exerted from this denser layer of sugar solution pushes the end of the widget, B, upward. The less dense end of the widget, A, that was in relative density disequilibrium due to the more dense end of the widget, B, being at the bottom and holding it down, now moves upward to a position in which it is in less of a relative density disequilibrium with the solution. Step C. The solid sugar continues to dissolve and the density and concentration gradients continue to form. As the density and concentration of the layers of sugar solution along the density and concentration gradient increase due to diffusion, the pressure that each layer exerts increases. This results in the widget being pushed upward from the pressure of the sugar solution layer directly below it. The series of diagrams below are a representation of how the more dense end of the widget, B, is pushed up by the pressure from the lower, more dense layers of the sugar solution. The red arrows represent pressure exerted from the sugar solution layers. The blue-white arrows represent air pressure. The widget is pushed upward until it is a position where the pressure from below is not great enough to cause it to move any further due to a combination of the pressure from above and the inertial mass of the object. What happened? The widget moved from the bottom of the sugar solution to the top. Note: it is appreciated that the density and concentration gradient will continue to increase, which will result in the widget eventually moving into a horizontal position. Any thermal energy generated by energy transfer will reach temperature equilibrium with the surroundings. Sugar at the bottom of the container. Dissolving, entropy increases. Sugar solution in density disequilibrium. Diffusion, kinetic energy. A density and concentration gradient continues to form. Diffusion, kinetic energy. Eventually, a stable density and pressure gradient in dynamic equilibrium will be formed. The vertical widget is in relative density equilibrium with the present density gradient of the sugar solution. The density and concentration gradient of the sugar solution increases along the entire gradient. The sugar solution around the entire length of the widget increases in density, as does its pressure. the end of the widget, B, being less dense than the surrounding sugar solution layer, is pushed upward by the pressure from the more dense sugar solution layer underneath it. Conclusion. The widget in a vertical position moved from the bottom to the top of the container. A density and concentration gradient were formed as the solid sugar at the bottom of the container dissolved into the medium, tap water sugar solution, and diffused. The density and concentration gradient continued to form as the solid sugar at the bottom of the container dissolved into the medium. The density of the sugar solution layer that the bottom end B of the widget was in became more dense than the end of the widget, resulting in a relative density disequilibrium between the object and the medium. The bottom end of the widget being less dense than the surrounding sugar solution layer was pushed upward by the pressure exerted by the more dense sugar solution layer underneath it. Due to the movement of the bottom end of the widget, the top end A of the widget was moved out of the layer of sugar solution it was in relative density disequilibrium with, and moved upward to a position which it was in less of a relative density disequilibrium with the medium. Note: it was being held in this position due to the more dense other end of the widget being the determining factor of the position of the widget within the density gradient of the medium. Why did the widget rise up when it was pushed down? When the widget vertically floating at the top is pushed down, it comes back up to the level position it was in before it was pushed down. What caused the widget to move in this way? Step A. The widget is in the sugar solution medium. The widget is in or close to being in relative density equilibrium with the sugar solution medium. Because the whole widget is not entirely suspended in the sugar solution, the less dense end of the widget is touching the top of the medium, it cannot be stated with complete certainty that the widget is in perfect relative density equilibrium with the sugar solution. The pink letters represent the sugar solution layer that has a similar density to that identically labeled letter of the widget. The widget was poked or knocked with a fingertip. A force was applied and energy transfer occurred from the external agent, the finger, and the widget. The widget accelerated and moved towards the bottom of the container. The moving widget possesses kinetic energy. Step B. The widget, when poked, moves to the bottom of the container. The widget is now in relative density disequilibrium with the sugar solution medium. The interaction, friction, between the widget as it moves downward through the more dense sugar solution layers results in the transfer of kinetic energy to thermal energy and the widget decelerating. When the widget hit the bottom of the container, the force of the collision resulted in the further transfer of kinetic energy to thermal energy and potentially sound energy. Step C. The widget experiences increased pressure when at the bottom of the container. The widget continued to move downward and into a greater relative density disequilibrium with the sugar solution medium. When the kinetic energy of the moving widget was transferred to thermal energy via the interaction friction with the lower density sugar solution layers, the widget no longer possessed the energy to overcome the upward pressure of the more dense sugar solution layers it was passing into. Step D. The pressure from the sugar solution causes the widget to move upward. The widget has been forced into relative density disequilibrium with its sugar solution medium. The pressure from the more dense sugar solution underneath the widget causes the widget to move in an upward direction. As the widget moves through the less dense sugar solution layers above the interaction friction, it results in the transfer of kinetic energy to thermal energy. Step E. Continued pressure from the sugar solution causes the widget to move upward. The pressure from the underneath layer of sugar solution causes the widget to keep moving upward. As the widget moves upward, it is pushed through the less dense layers of sugar solution that are exerting less pressure relative to the more dense lower down layers of sugar solution. This interaction, friction, between the widget and the medium results in the kinetic energy of the widget being transferred to thermal energy and the widget decelerating. Due to the density and pressure gradients presented in the sugar solution medium, the upward force, pressure, is greater than the downward force, pressure, and the inertial mass of the widget, which results in the widget moving in an upward direction. Step F. The widget reaches relative density equilibrium or near to it with its sugar solution medium. The widget rises to the top of the sugar solution. The widget strikes the surface of the water, and the surface tension of the water combined with air pressure prevents the widget from moving upward any further. The upward and downward forces on the widget are balanced, and the widget is in relative density equilibrium or near to it with the sugar solution medium. What happened? The widget was pushed to the bottom of the sugar solution and rose back up again. Note: it is appreciated that the density and concentration gradient will continue to increase, which will result in the widget eventually moving into a horizontal position. Any thermal energy generated by energy transfer will reach temperature equilibrium with the surroundings. Widget in relative density equilibrium or near to with the sugar solution, high entropy. The widget is pushed downward, force applied. Widget has kinetic energy. The widget moves downward. The widget is in relative density disequilibrium, lower entropy. Widget losing kinetic energy. Sugar solution gaining thermal energy. The widget is at the bottom of the container, low entropy. The entire length of the widget is less dense than the layers of sugar solution surrounding it. The widget is pushed upward by the pressure from the more dense sugar solution layer underneath it. Force applied. Widget has kinetic energy. The widget moves upward, higher entropy. Widget losing kinetic energy. Sugar solution gaining thermal energy. Widget back up to the top of the sugar solution and in relative density equilibrium or near to it with the sugar solution, high entropy. Conclusion: when pushed downwards, the widget moved back upward because the pushing force, pressure, and its vector from the finger transferred kinetic energy to the widget, causing it to move downwards through the sugar solution, putting it in relative density disequilibrium. As the widget moved downward against the increasing density and concentration gradient of the sugar solution medium, its interaction, friction, with the medium resulted in the kinetic energy of the widget being transferred to thermal energy and the widget slowing down and stopping. The dense layers of the sugar solution pushed, pressure, the relatively less dense widget upward. The widget's interaction, friction, with the above less dense sugar layers it was moving through resulted in a transfer of kinetic energy to thermal energy. The upward force pressure from the sugar solution on the widget is balanced by the surface tension of the water and air pressure and the inertial mass of the widget, resulting in the widget being in relative density equilibrium or near to it with the sugar solution medium. Summary: the mechanism for the widget going up and down when pushed. 1. The object starts in relative density equilibrium, or near to it, with its medium and surroundings. The domain, the object and the medium surroundings, has a high entropy at this point, a limited ability to do work as the energy of the domain is dispersed. 2. An external agent event results in the application of a force, in this instance pressure, and the transfer of kinetic energy from the external agent event to the object medium. 3. The moving object is no longer in relative density equilibrium with its medium and surroundings. The medium, moving, and surroundings are no longer in relative density equilibrium with the object. 4. The kinetic energy of the object moving is transferred into thermal energy as it interacts, a force friction, with the medium, moving, and surroundings. The thermal energy is lost to the surroundings and thermal equilibrium is established. 5. The domain has a lower entropy at this point compared to before the input from the external agent event. 6. The object and the medium and surroundings proceed back towards a position of relative density equilibrium. 7. The application of a force, pressure, by the medium results in the transfer of kinetic energy between the object and the medium. 8. This results in the object and medium moving, and their interaction, a force friction, results in the transfer of kinetic energy into thermal energy. The thermal energy is lost to the surroundings and thermal equilibrium is established. 9. The object and medium return to relative density equilibrium and the domain returns to having a high entropy. Domain in relative density equilibrium and high entropy, possessing limited potential energy. Force, example pressure, large one-off force or multiple small sustained forces for a time from an external agent. Energy transfer, one-off or sustained for a time from an external agent. Medium, object, either or both, moving. Medium and object, either or both, kinetic energy transferring to thermal energy and possibly other forms. Domain in relative density disequilibrium and low entropy, possesses potential energy. Force, example pressure, large one-off force or multiple small sustained forces for a time from an external agent. Energy transfer, one-off or sustained for a time from an external agent. Medium, object, either or both, moving. Medium, object, either or both, kinetic energy transferring to thermal energy and possibly other forms. Domain returns to relative density equilibrium and high entropy, possessing limited potential energy. A process profile diagram for the widget going up and down when pushed. Please pause to examine this slide carefully. Can this mechanism describe the egg observation? The egg was placed in a salt solution that had an established density and concentration gradient. The egg was left to obtain relative density equilibrium with the salt solution. The A and B show the top and bottom position of the egg relative to the density layers of the salt solution. Note: it is not known whether the starting salt solution was saturated or not. It is assumed it was not saturated and more salt will dissolve into the solution. When solid salt granules, mass, were added to the salt solution, they sunk to the bottom of the container. The solid salt granules joined the layer of solid salt already at the bottom of the container. The solid salt displaced the column of salt solution upwards by its volume. See Archimedes' principle. The column of salt solution would have risen if it wasn't obviously observable. The new added solid salt granules at the bottom of the container affected the already existing density and concentration gradient of the salt solution within the container. Every layer of the density and concentration gradient became more dense and concentrated as the new solid salt granules dissolved into the salt solution. The layers that the egg was suspended in became more dense and concentrated, and the egg rose higher in the solution. But what caused the egg to rise? The addition of the mass of salt causes the density and concentration of the salt solution layers of the gradient to increase, resulting in the egg being in a temporary relative density disequilibrium with the medium. The salt solution layers the egg is suspended in have become more dense and the layers are exerting greater pressure, force, on the egg, which causes the now relatively less dense egg to be pushed, forced upward. The egg is pushed, forced upward, until it reaches a position of relative density equilibrium and is suspended in salt solution layers whose pressures are not high enough to force the egg up any further. Why did the egg go upward? The egg was pushed upward as that was the only direction it could proceed. The egg can't go downward as the higher density salt solution layers underneath it are pushing up against it for the highest pressure. The egg can't go sideways as the high-density salt solution layers around the egg at this level is pushing against it from all horizontal directions at a high pressure. Thus, the lower pressure area above the egg is the only direction the egg can be pushed to. Why the egg went up? Mass, G, of salt added to the salt solution medium. Anthony's statement: this, the salt, altered the amount of mass in the medium. The density and concentration gradients of the salt solution increases along the entire gradient in an upward direction. Anthony's statement: the only place the change in mass can go is up. The increased pressure from the increased density and concentration gradient layers of salt solution below and to the side of the egg pushes the egg upward. Anthony's statement. And cause pressure that pushes the egg up from underneath. The force is pressure caused by adding mass below the egg. The cause and effect chain. Increased mass, salt added to the solution, results in increased density of the layers along the density gradient. Layers of salt solution underneath the egg become more dense. The layers along the density gradient exert increased pressure. Layers of salt solution underneath the egg exert more pressure than the layers above the egg. The effect is the egg rises in the solution. Clearly, without the addition of the mass of sugar, the widget and egg would not have risen in the medium.